Alright, so you got two experiments today. The first is summarized on the back board, and the second is summarized up here on the left side of the front board. In the first one, you're going to, as he has mentioned, you're going to be just determining the capacitance of these two capacitors right here, putting them into various combinations with these resistors right here. All these combinations essentially saying resistor 1 and capacitor 1, resistor 2 and capacitor 1. All these combinations are both on the backboard as well as in the experimental procedure section of the lab manual. You'll effectively charge up the capacitors and discharge them through the resistors over some period of time, analyzing that resulting exponential decay of the capacitor's voltage as a function of time to back out then the capacitances, right? That's the whole first experiment. The second experiment, again summarized here on the front board, you're dividing the charge between the two capacitors, seeing how the voltage difference between before you divide the charge between the two capacitors and after you divide the charge between the two capacitors changes. After you do it a bunch of times for a bunch of different combinations that I'll cover later on. So first, at least following the lab manual, first you can go ahead and find the resistance values for the resistors, very much like last week, right? You just take it to the ohm meter, connect the resistor up. Just remember that there are, again, units for whatever the actual resistance is. And then you can also, for your comparisons later, figure out the capacitance of your capacitors to treat these as your quote-unquote actual values that you will compare all your experimental data to later, right? And to do that, you'll stay on the same, stay with the ohm meter, but use the little yellow toggle button to switch to capacitance. This is noted up on the top right-hand side of the board, and you'll see the capacitance of this one that claims to be 330 microfarads is actually around 373 microfarads. Again, the unit is right up in the top right corner of the multimeter here. There is some manufacturing tolerances. It's close enough. This will be your actual value, right, that you'll compare to your range of data later on. And then after doing that, you don't need the multimeter for the rest of the lab. Something to note, right, you have two capacitors, two resistors. Call one R1, call one R2, call one capacitor 1, call one capacitor 2. Doesn't matter which one's which, just be consistent throughout, be descriptive so that you know which one's which if you need to go back and retest some things. And then you also have this red wire here, which is essentially a wire with no resistance, right? So effectively no resistance, right? So if you were to touch it on either side of the capacitor like this, you will discharge any charge that is currently built up in the capacitor, setting the voltage effectively back to 0, which you will do mostly in experiment 2. Then for each setup, you'll have a circuit that looks like this. You got batteries at the bottom that provide your voltage source, essentially your power source. You'll have the ability to have a switch over here that makes a circuit of just the bottom portion, or if you throw the circuit to the top, just the top portion where current can flow. Let's see, this looks like the circuits in figures 5.4 and 5.5. The diagram in 5.4 is there to show you essentially how to set up the different resistors and capacitors and where you should put them. Then before we go further, in Capstone, you'll have something like this, where on the top left-hand side, you'll have voltage as a function of time. On the bottom left-hand side, you'll have the natural log of the voltage as a function of time, essentially trying to linearize that exponential function. And then on the right-hand side is a data table that is connected to the voltage plot on the top, where if you were to select data, it would highlight the data in the data table. You probably won't use it because we'll be using other tools, but it's there if you need it. Before starting anything, you can press record and notice, oh hey, the voltage may be not the voltage sensor, which is connected to either side of where you're going to put the capacitor later, the voltage sensor is showing a non-zero voltage right now. So like last week, make sure to zero out the sensor with the little 0 and the 2 yellow arrows right there. It zeroes it out. We're back to 0 volts. Cool, sensor's good, and you can move on to building out your circuit. If I want this one. At this point, you take your capacitors. In this case, will go in the, just slide into these springs. Then you take one of your resistors, slide it into one of the set of springs on the top. Doesn't matter if you do the bottom or top of this block. Doesn't matter if you do the bottom or top of this block. They're both all wired up to make the connection across the block there, right? But essentially now, if I was to throw the switch down, we have a battery and capacitor circuit, and if I was to throw the switch up, we'd have a capacitor resistor circuit, or resistor-capacitor circuit. So then, with the capacitor here, with the resistor here, actually I'm going to use the big one for now. We can go into capstone. If I was to press record, I'm centered roughly around 0. There, definitely 0. Once you zero out your circuit, it should be fine. There seems to be a little bit of charge on this capacitor maybe. But if I was to throw the switch down, there is now voltage charging up this capacitor. If I throw the switch to the top, the capacitor is now discharging through the resistor over some period of time, and we're seeing that exponential decay. And you'll do this 5 times for each of your 6 resistor capacitor circuits. But you don't have to press stop. You can just wait until the voltage here in the top plot, shown in green, gets down to at least 10% or less of its initial voltage. So if you're starting at 3 volts, let it get down to at least like 0.3 volts, so that you have enough data to characterize the decay without waiting, infinite amount of time. But then you can just throw the switch, charge the capacitor back up, throw the switch back. You see the decay happening again. I may not have fully thrown the switch earlier. I guess I did. But say if it got all the way down to 10% of the charge, I could just throw it down. It starts decaying. I would bring it back up. It starts decaying again. I would throw it one more time. And I would have the 5 full decays. After which you could then stop it. It'll look like something like the drawing on the bottom left-hand side of the board in the back. Right, you'll have effectively 5 decays all on one plot. That is your 5 trials for that given resistor capacitor case, right? So for the first version of analysis, the graphical analysis, you're using the natural log plot of voltage as a function of time down at the bottom, and you can reminder for capstone, right? You can scroll in and out on the different axes to zoom in just the axes individually. You can zoom in and out, and if you need to fit the whole data set, you can press the top left button on the screen here to get you back to wherever your data is. So on the bottom plot, use the highlight data tool if the computer keeps up. And you want to highlight enough data to make a fit, right? You'll have a linear fit, but you want to make sure that you're actually along just exponential decay and not getting too close to 0 voltage, where natural log of 0 goes to getting all messy towards negative infinity. So on the top toolbar, there's this little 4 black arrows pointing together. You click the Add Multi-Coordinates tool, and you can see here now I can show both the voltage and whatever time that is associated with that voltage. So you want to go to around 3 volts, since 2 AA batteries adds up to around 3 volts. You can line up the bottom plot to around that. Then you can drag this tool over to around 10% of that, so say 0.3 volts. Take your data highlighting over to just that range, and now you have a linearized portion of just the exponential decay that you can then use the polynomial fit. Right, we're doing a linear fit here. It should automatically pop up when you select the data highlight tool. If not, just remember that it's that tool there. And this M, this slope here, is the slope that you're going to use to back out the capacitance for the graphical method. But on the bottom right-hand side of the front board is a note to increase the number of significant figures for the slope. Since it doesn't actually save it in Capstone, that setting, go to the settings of the curve fit editor here, go to numerical format, go to coefficients, and increase the number of sig figs to at least 5. And then you have resolution that is more appropriate for the amount of data that we're fitting right now. Solve for the capacitance, right? That's the graphical method. You're using the fit of the bottom plot. The half-life method is going back to just the top plot, where we're focusing. We can use this multi-coordinates tool again. Go to somewhere before, right after the decay starts. So if you want to zoom all the way in, you could get right up close to it. Say we have 3.14 volts. We want to then, that would be your initial voltage, and so then that has an initial time. You then go and find the half voltage, essentially 3.14 divided by 2 would be 1.57. So I go down to 1.57 volts, which is around here, and I would have a different time that's associated with the voltage, that's associated with half of the initial voltage. And so then this would be your, as described in the lab manual, the half time, different than the half-life. The half-life is inherent to the exponential decay. Half time is just saying, hey, this is the time in Capstone where the voltage has reached half of its initial voltage. Yeah? Take the difference between this half time, final time, right? And the initial time when the voltage was at whatever you set it to be, that initial voltage. And then that time difference is that half-life. From that half-life, you use equation 515 to back out the capacitance. Same equation that is written on the board at the front. You do that for each of the 6 resistor-capacitor circuits. You do 5 decays for each of those. That's the majority of your data taken today. Reminders of the different spots to look at is also depicted on the backboard. In the right-hand side of the board, try to draw out examples of these plots, right? You'll have averages. You'll take the standard deviation, and in this lab, we'll do the standard error as the uncertainty. It's all there, relatively clear. If you have questions, let us know. Then the second experiment is now, instead of having a capacitor and resistor, we take the resistor out, take the other capacitor here, and throw it into the top set of springs. I'm going to switch them for demonstration purposes. You don't need the resistors anymore. To start, before you take any data, use the red wire, discharge both of the capacitors just to ensure that you're starting out essentially fresh. The second experiment has effectively 4 parts. The first and second are with the capacitors in this configuration. The third and fourth parts are essentially with the capacitors just swapped. Essentially repeating the same thing, but with the capacitors in the other order. This is again summarized on the front board. You're doing effectively 5 trials of each of these 4 cases. But again, like we've done in the first part, you can take all 5 trials all in the same data run in Capstone at the same time, right? So you press record. We see that we have currently no voltage being measured across this capacitor. I throw the circuit down, and now we have around 3 volts charging up this capacitor here. And then if I was to throw the switch up, the charge here has been divided and shared with the capacitor here on the top. We've dropped in voltage, And then if I was to throw the switch again, I'm recharge the bottom capacitor, and then I throw the switch back up to the top, share the charge on the bottom capacitor with the top capacitor, and we have built up a higher, essentially shared voltage. You do that essentially 5 times, you get it all on one big plot that you can then analyze for your 5 trials for that case. Cool, you're done. To find the, you're going to be looking at essentially the voltage difference between here and here. This voltage drop in the top plot here, we're looking at essentially right before you share the charge, you'll have some voltage. In this case, we're having about 3.15 volts. That would be your initial voltage, and then the final voltage is whatever the voltage is after the charge has been shared between the 2 capacitors. In this case, 0.7 volts is our final voltage, and then you're going to be looking at the difference. You'll take the difference between those 2 voltages, see how those change as you flip the switch back and forth a bunch of times. That's the first part. The second part is just doing that same process, but before you throw the switch back up to the top, you just make sure to discharge the top capacitor. You do that 5 times, and then you take the capacitors, you swap them, you repeat, and then you're done.